If you take an ordinary ball bearing, cut through the outer race, and put it back together, something genuinely interesting happens. Let me back up and explain from the start. The idea behind a ball bearing is actually pretty simple. You've got an inner ring, an outer ring, and a set of spheres sandwiched between the two, held in place by a cage. In theory, when one ring turns relative to the other, friction is minimal because everything rolls. This particular ball, by the way, came from a massive bearing that used to sit inside a now decommissioned wind tunnel. Anyway, ball bearings have a built-in limitation. If you push the inner ring against the outer one, you'll feel a bit of wobble. That happens because manufacturing a perfectly fitted part is essentially impossible. This is the real world, and nothing is truly perfect. I'm using a special high-clearance bearing here to exaggerate the effect for this demonstration. But the same thing shows up in any bearing to some degree. The fix is to apply opposing axial forces to the two rings to soak up that wobble. In engineering terms, this is called bearing preload. But here's the catch. It sounds simple enough, but you can't apply that force without also restricting rotation. If I use a spring to generate that force, for instance, I have to hold an opposing force against it with my fingers. The moment I let go, the preload disappears. If I thread a nut onto the shaft, and I use shaft loosely here, since it's really just a bolt to keep the spring compressed, the force stops passing through the bearing balls entirely, so the bearing stays wobbly. If instead, I use a dishwasher that only contacts the outer raceway, tightening the... So what did all this actually accomplish? Once reassembled, the bearing still functions the same way it did before. Sure, part of the outer race is now missing. But under an axial load, that particular section of the raceway never carried any load in the first place. Here's the clever bit. By applying force directly to the outer raceway, we can now preload a single bearing on its own. That's the theory, but does it actually hold up in practice? To test it, we fitted this modified bearing into Alistair's milling machine. Like most machine tools, the table on this mill is moved by a feed screw, engaging with a nut, turning the screw pulls or pushes the table. The ends of the feed screw here are each supported by standard ball bearings. Before installing the split bearing on the y-axis, this is how far the handle rotated before the table actually started moving, somewhere between 0.1 and 0.2 millimeters of play, meaning that much backlash existed in the system. Cutting down backlash matters a lot for certain machining operations like climb milling. So wouldn't it be great if we could shrink that number? With the new split bearing installed and preloaded using a shim, the improvement is dramatic. Backlash drops to somewhere around 30 to 40 microns. The motion feels smooth and clean, and there's even a noticeable improvement in cut quality once the new bearing is in place. We originally stumbled onto this whole idea while going through the manual for my Shoblin crossslide. Looking at the cross-section diagram in that manual, it appears to use exactly this split bearing concept. After digging around a bit, the closest commercially available equivalent seems to be something called a 4-point contact bearing, though I'm not entirely sure whether those can actually be preloaded. Maybe someone in the comments can clear that up. This is the high clearance bearing I mentioned earlier, specifically designed for high-speed use, with extra room built in to accommodate the thermal expansion issue I showed before. I ran this one through an ultrasonic cleaner to strip off the factory grease, and look how long it spins afterward. Compare that to the same bearing straight out of the packaging. Stripping the factory grease completely actually made it spin noticeably better. Now, if I add just a single drop of low-viscosity oil to the clean bearing, it practically grinds to a halt. Do the exact same. The thing between two flat metal surfaces, though, and you get the completely opposite result. Strange, right? Both setups involve metal-on-metal contact, so why does a sliding block behave in exactly the opposite way to a rolling bearing? And should ball bearings even run without lubrication at all? Let's start with the metal block. When two metal surfaces touch, all the tiny microscopic peaks and imperfections on each surface generate friction. Add a drop of oil, though, and it forms a thin film that keeps those surfaces from touching directly, which cuts friction significantly. That's called hydrodynamic lubrication. And if you match the right viscosity to the sliding speed and load involved, you can achieve remarkably low friction. This behavior is captured nicely on what's known as the Stribeck curve. As you move along the x-axis, you pass through different lubrication regimes. The lowest friction shows up right when the lubricant film is just thick enough to separate the asperities on both surfaces, but not so thick that viscous drag starts slowing things down. So why doesn't the same thing happen with the bearing? I think it comes down to the fact that the balls are rolling, and rolling motion already produces very little friction on its own. The moment you introduce a lubricant, viscous forces start to dominate instead, and the bearing slows right down. Now, you might be wondering why bearings come pre-greased from the factory at all. Well, about 10 seconds ago, when I said the balls roll, that wasn't quite the whole truth. Under load, the balls and raceway actually compress ever so slightly. It's completely invisible to the naked eye, but it's enough to introduce a tiny amount of microscopic sliding alongside the rolling. So, should you actually run lubrication in your ball bearings? In the vast majority of situations, yes, absolutely you should. But in low-load applications where minimizing viscous drag really matters, fidget spinners being the obvious example, it might actually be worth stripping out the factory grease and seeing what happens. A big thanks to our patrons. Videos like this one simply wouldn't be sustainable without your support. And thanks to everyone who stuck around and watched all the way through. Hopefully you picked up something interesting along the way. See you in the next one.